Hello, everyone. Welcome to our second session of blockchain speaker series. And today it's my pleasure to introduce one of our own, John Long, is a UCD student, and he's been one of the most active folks in the blockchain at Davis. And he's a kind of the head instructor. So he has official title of head instructors, and had the opportunity to know him for the past few years, and he's an excellent speaker as well. So he's going to talk about Ethereum, sort of the basis of the Ethereum, or how it works, and he's really, I think, a lot of expertise on this subject. So with that, John, please take it away.
Thank you so much for that wonderful introduction. It's been a pleasure to work with Professor Sadogi, and I'm incredibly happy to be in front of you guys today. So without further ado, I do have something prepared for sort of like an introduction to how Ethereum works. Let me share my screen, and do let me know if you can see it. Okay, let's go ahead and hit share. Now I have to drag everything to the right. I will go ahead and hit present, the pointer, and I also have the chat open. So if there are any questions, feel free to raise your hand or go ahead and put it in the chat. I'm more than willing to answer those. So with that being said, as Professor Stogie mentioned, I'm the head instructor for blockchain at Davis. I'm coming up on my, it's already been over 2 years now. So I'm ecstatic to do something like this. So just a brief overview of what I'm hoping to cover today is to provide some historical context to sort of put Ethereum where it belongs and maybe where you understand the kind of cryptocurrency environment, and then build off of some existing knowledge from maybe the prior lectures you've had, or I see that on the course schedule there is a talk on Bitcoin, which I think will be very conducive to helping you understand how Ethereum works. But on top of that, although there are like some places where they're related, there's also what I call like the secret sauce. So there are a couple components about Ethereum that make it really stand out as a unique blockchain environment. And along with that, amazing sort of innovation, there's of course some shortcomings, and I have maybe one or two concluding remarks to give you some food for thought. So without further ado, let's go ahead here. So I'm going to go way back in time. So we're going to go talk about some very early cryptocurrency history. So around 2008, 2009, Bitcoin got launched by the kind of mysterious Satoshi Nakamoto. To this day, no one really knows who he is. There are some far-flung hypotheses, but nothing solid. But Bitcoin was pretty revolutionary in the idea that it was living proof that you can accomplish a decentralized consensus. It is feasible, it is capable of being self-sustaining, and it works. And from the moment Bitcoin was born, we see what I always call the kind of altcoin flood. So in the subsequent 4 to 5 years, we see alternative cryptocurrencies. At first, people would just fork the Bitcoin code and play around with it. But they added a bunch of new features as well to address some of the concerns that they were having with Bitcoin. For example, incentivization. So the nodes that host copies of this blockchain, why aren't they being rewarded as well? And some coins tried to implement features for that. Or centralization. There are stories these days of like huge mining operations in China, like Bitcoin mining operations, and it's a concern for the security of the network as they gain more and more power. Or a more remote concern, but still warranted, is what if the hashing function that Bitcoin relies on, what if that gets compromised? So then you see the birth of X11, X12, X13. I think they even managed to get up to X17. So they daisy chain multiple hashing algorithms to try and deter this, although it didn't gain much popularity, and you can pretty much treat them as being dead at this point. So around 2014, that's when we start to see the birth of Ethereum. So it was launched by Vitalik Buterin. I think he's in his mid-20s, very young guy. So if you guys take this course and you get out of college, there's plenty of stuff you can do in the realm of blockchain technology. But Buterin had the idea of leveraging this blockchain technology for this decentralized application. So it's an application that apps that do not need to rely on a single provider for access. So a single provider is like we're using Zoom right now. Zoom is hosted on the Zoom company server, or Google is you have to go to a central location. And if that gets compromised or fails or data gets leaked, then it becomes very problematic. So we can he had the idea like let's go ahead and leverage what blockchain is good for, which is that decentralized capabilities for applications. And Buterin also recognized the need for a more powerful scripting language. So in this picture below, this is what, like a very, very simplified Bitcoin transaction. But the idea is that although Bitcoin does have its own programming language, it's literally just called script, it's not Turing complete. The only reason that language exists is for complex transactions. So maybe like, two people want to send money to three people pending a certain condition or a signature. But you can't write applications with it. So it's a very handicapped in that regard. But Buterin was like, well, if we have something more powerful, then we can have these applications which can live in this blockchain environment. So with that being said, the way Ethereum has grown is through a kind of series of milestones. So it has a very sort of rich history. I remember when Ethereum was still in sort of testnet phase. So it hadn't even become a viable currency. I was already messing with the language. Some very interesting stuff there. So Frontier and Homestead are sort of the code names. That was the initial release. They just want to make sure that everything is working properly. And then we see sort of Byzantium and Constantinople, which are designed to address certain scalability problems. So as more and more people use Ethereum, we start to see some network latency problems and concerns over security. But as I near the end of my little presentation here, I want to pay attention to Serenity, or Ethereum 2.0, which is a major kind of upgrade to the security and throughput that this network has. Some of these updates have required hard forks, and a hard fork is essentially just a protocol upgrade. So the way the whole blockchain systems work is that all the nodes have to be in agreement. Everyone has to follow the same protocol. But as a developer, if I implement a new protocol, then usually what happens is I have to sort of get all the other nodes to comply. So they have to upgrade their software, and all the other nodes become invalid. So it's this constant kind of game of catch up. And Ethereum has been sort of chugging along with these in order to implement much needed infrastructure in that regard. So I know you guys have some pre-existing knowledge of Bitcoin. So in many regards, if you were to look at Ethereum from a purely architectural standpoint, you could get away with saying that they are similar in some regards. So it still has a main blockchain, and it still has the same kind of hash linking technique. So one block holds the previous hash of the other block, and it's this chain. So if you tamper with one block, everything prior to it becomes invalid. And it's still possible to have orphan blocks. So if two blocks get submitted at the same time, and we still see the kind of, you still see the same, they still get accepted, and there's kind of a race to see which chain becomes longer. There is still an incentive model based around mining, so expending computational power to verify transactions. And there's still nodes. So nodes have to hold copies of this blockchain, and they are responsible for verifying and distributing that blockchain to ensure that the entirety of the network remains synchronized. So there are your similarities, but with that being said, the similarities end then and there. So there's plenty of new stuff to explore. And that secret sauce that I alluded to in the beginning is the smart contract. So we'll start with a traditional contract. So it is just an agreement between at least two people, and it has to be recognized, or it's usually recognized by a trusted third party. So, if I were to make a financing deal between me and a small business, I might go to a bank, and the bank would be like, okay, this checks out, everything's legit. And if someone breaks that contract, then there are, there are punishments, and there's a way to verify the validity of such an event. But the traditional model does have one glaring flaw, and there's plenty of all this stuff on the news, is what if that third party gets compromised? What if I bribe that third party? And how much vetting, how much like verification do I need to make sure that this third party is good enough? Like, there's no guarantee that they will not run off with my money or violate that contract. So in around the 1990, 1991, I believe is the exact time, Nick Szabo, so he's a legal scholar and a computer scientist, he comes up with this idea of a smart contract. It's the same idea. It's still an agreement between multiple parties, but instead of having a compromisable human or some other human-based entity as the enforcer, we now have a machine or a computer enforce it. And the example he gives in his paper is a vending machine. That's the earliest idea of a smart contract. You give the tokens or your quarters in, and then you get your bag of chips out. It is, and it's enforced by a bunch of circuits, no human intermediary. But we want to take that one step further, knowing what we already know about blockchain here, and we want to have contracts that are enforced by blockchain tech and Turing completeness. The Turing completeness being the scripting language here that I mentioned earlier with Bitcoin script not being good enough and lacking the ability to develop applications on. So here's how smart contracts sort of work in Ethereum. If you have familiarity with the platform, you'll notice I'm glazing over a large number of technicalities and some of the architecture. But then again, it is my goal to give a higher level overview of how Ethereum works and what makes it so prominent in today's sort of cryptocurrency or crypto environment, I would say. So how these smart contracts work is that the developer will compile a contract into something the nodes on the blockchain network understand. So the analogy I want to give here is if you've ever seen an actual legal contract, it's all in this sort of legal, very high English and lawyers are there to interpret it and whatnot. So the same thing goes for Ethereum. We have high level languages like Solidity and Viper. But these high-level languages that you write your contract in get translated into EVM opcodes. And I'll tell you what EVM is in a short moment. But with that being said, what happens is the compiled code piggybacks on a transaction. So if I'm submitting this contract for enforcement, I want to publish it in a sense, it sort of gets wrapped in this transaction and then sent off to the network. Now, the Ethereum nodes are smart enough to realize, like, wait a minute, this isn't, a money that's going to anyone in particular, but it's rather it is it's a contract or a unit of execution in itself. So it's not meant to, it's not meant to be receiving or sending any money like a normal user. So what the nodes do is that smart contract gets granted its own address. So that address is how you interact with the smart contract. It's how you find it on the blockchain. It's how you will invoke some of its functions or built-in properties. And one thing that I'll have to emphasize here is that all the nodes, every node on the network will execute that contract. It isn't, half the nodes or a selective number. All of them will execute the contents of that contract. So we'll want to, stay tuned on how the Ethereum nodes differ from Bitcoin nodes, because for now, I imagine you're assuming that the Ethereum nodes are just, holding a copy of the blockchain there. Let's see. So with that being said, now we can jump into the kind of architectural considerations for these Ethereum nodes. So the Ethereum nodes, like Bitcoin nodes, they hold copies of that blockchain, but they're also capable of executing code. So that's a rather unique kind of feature there. What would be an example contract? Like, what are people agreeing on? Okay, so let's say that maybe I'm starting a business and I want to issue a number of like limited tokens, and those tokens would represent ownership in my business. Let's say, I don't know, I'm selling apples. I'm an apple farmer. So what the contract does is when it detects that you've sent the contract the Ethereum, the Ether, it will issue out the tokens to you, and you become an official shareholder in my apple farming business. Or you can have multiple parties, and you can make escrow applications in essence. So maybe a certain number of criteria have to be met, or a number of people have to give their digital signatures off onto that contract, and then the contract will distribute a locked sum of money. So those would be some examples of some example contracts. I hope that answers your question, Zach, but feel free to keep asking it in the chat. I'm more than happy to answer them. So each of these Ethereum nodes possesses that EVM that I mentioned earlier, and EVM stands for the Ethereum Virtual Machine. And this virtual machine is incredibly weak. Like it only has opcodes or instructions that are a byte long. And it doesn't even use all of them. So we're talking about a miniature computer that has less than 255 instructions. To put that in context, modern Intel, AMD, and ARM, we're talking thousands, maybe tens of thousands of units or of executable instructions. The machine is stack-based. So yeah, it's almost like if I had a stack of papers, I push data onto the stack and execute on that singular stack. So very limited memory model there. And it's sandboxed. And this is very important because we don't want people to write contracts that can, hack your computer or leak your information. So they are kept away from the internals of the computer it runs on. And also, this is part of the Ethereum model here, concurrency versus parallelism. So, once again, these contracts are run by every single node here. Oh, it looks like I'm looking at Sean's question in chat. Is there a limit to the length of the programs? Could I maliciously upload an infinitely long program to halt all of the nodes? That is an excellent question. Yes, there is a limit. I'm about to get to what that limit is enforced by, or what the limit looks like. You could potentially do something like that if you have like there we go, Cameron. Nice, Cameron's here. Cameron is hinting at it. There's this thing called gas that is there to prevent such things. And also, if you wanted to do something like that, you would have to have like all the ether on the network, which is impossible. So I'm going back to concurrency. What I'm trying to get at here is that people mistake concurrency with parallelism. So you would think like, oh, if I have my smart contract, maybe I can split it up on different nodes, and you can't. It runs everything at the same time, which is great for concurrency though. So if half the Ethereum network failed for some reason, the other half can still keep chugging along and running your application or smart contract. That's great. But it cannot computationally split up, different things there. So you can't think of Ethereum as one big old supercomputer in that sense. And here we go. This is what Cameron was alluding to. Thank you. This is sort of the idea of gas and ether. So ether, as I hinted at earlier, is the name of one unit of the Ethereum crypto. So, like Bitcoin and Bitcoins, and Ripple has its own and I guess you would call them droplets or ripples, I guess. I'm not too familiar with that unit of currency. So ether is just, one unit of the Ethereum cryptocurrency. But there's also this other thing called gas. And gas is what I would call a unit of computation. So those smart contracts are coded, right? They have a number of, sort of opcodes and instructions they execute. Each instruction has an associated gas cost. So for example, if I wanted to add two numbers, that might be 1,000 units of gas. Or if I wanted to take the hash of a string, that might be 12,000 gas, just an example. And you can also have static and dynamic costs. So addition, like adding numbers, may be a static cost. But hashing, where the size of the data is variable, may very well be a dynamic cost. So every byte the amount of gas grows on you. And you can purchase gas via Ether. The network does this automatically, so you can't go onto some crypto exchange and say, like, I would like, I don't know, 10 million gas for 1 Ether. You can't do that. The blockchain internally handles that. And it's the smallest unit of Ethereum is like I believe it's like a gwei, as it's called. So that's usually when market people talk about, like, oh, how much is gas, they will say it's like maybe some number of gwei. And why does Ethereum bother doing this? Why do we want to separate this unit of computation from the currency itself? Isn't this more hassle than it's worth? Well, the idea behind this is that we want to separate the utility from market volatility. So imagine, like, you're using your laptop, and all of a sudden, like, just because the NASDAQ lost 1,000 points, you can't do anything on your laptop anymore. Like, oh, it looks like you are forbidden from doing any work. And that's sort of the idea here. Cryptocurrencies, as many of you may be familiar with, are notorious for being very volatile. So the idea behind this was they didn't want smart contracts and applications to suffer from this market volatility. So the idea here is that if we separate the unit of utility from the sort of token or the unit of currency itself, we can kind of cushion the market volatility from affecting the actual network's computational capacity too much. So the analogy that I always love to give here, and this is not my own, unfortunately, is that you need gas to drive a car, but you pay for that gas with money, cold cash or a credit card. So that's the analogy that I like to think of between gas and ether. Now, with that being said, you guys have like this rough overview of smart contracts, being able to run this kind of highly concurrent code and whatnot. Now it becomes a matter of dealing with these decentralized applications. So smart contracts, as I mentioned earlier, have their own addresses. You can invoke them via transactions, and it doesn't matter where the transaction comes from as long as it's valid. So smart contracts can reach out to other smart contracts, and as a result, you can sort of chain together or lump together these smart contracts, and you can have multiple contracts work together to create a decentralized application. And I mentioned spoke and hub here. And the idea behind here is you can have like one smart contract be responsible for, dealing with the front end. And then the hub contracts are the ones that the spoke will sort of reach out to, and it will, they're responsible for smaller units of execution, like object-oriented programming, for example. And with this idea in mind, now we can have these decentralized apps. So they run entirely on the Ethereum blockchain, and they don't need a single server to rely on them. So if, as I mentioned earlier, if half the Ethereum network vanished overnight, no sweat, your application is still up and running. Whereas if Google servers vanish overnight, well, then you can't use Google, and you're going to have it's very cumbersome for the user. And one of the pioneering applications that has come out from DApps, or decentralized applications, are DAOs, or decentralized autonomous organizations. And the idea is that we can have certain organizational rules codified as smart contracts. So some examples I put out here is that managers can only get paid, they get paid via this contract, and the payment is conditional on maybe some vote by shareholders or some criteria being met. And it allows for a much better integration with tokens or voting. So many of these DAOs have a public component where, like, you as a stakeholder get to decide, should this company work on project A or project B? I can use my token on this smart contract, and that will sort of notify the organization, okay, this is what we're going to work on, and this is where our payment is locked up as. So only until the organization satisfies the condition that they finish work on project A, then they will get paid for their work. So the smart contracts do that all. There is no human entity, pulling the strings here, and it reduces a lot of the problems with having a human intermediary, such as corruption or things like that. With the smart contract being the main focus, I wanted to talk about a number of sort of architectural peculiarities that you will encounter when working with Ethereum. So one of them is that the Ethereum block size is not fixed. So that might be a little unusual because blockchain, or not blockchain, Bitcoin has a fixed limit on that size, but it's 1 megabyte, although with the segregated witness update and a number of roiling controversies, there's been some variations where they've expanded it to 2 megabytes, 4, 8 megabytes. But the Ethereum block size is dictated on gas. So it's how much gas all the transactions and data in the block that's being worked on contains. So right now they're around 10 million gas right now, or no, the limit, the block limit is 10 million gas. So that is, and remember, different opcodes, different instructions in a smart contract can have different amounts of gas. So as a result, you can have varying block sizes. And I think last time I checked, it's like 20 to 30 kilobytes. So much smaller than what Bitcoin has for one block, which means those blocks get generated faster. So faster transaction times as a result. Also, miners get to collectively vote on what the gas limit per block should be. And the reason that is you got to remember that gas, as I mentioned, is a unit of utility, a unit of computation. So the miners that are doing all this work, that are verifying transactions, if there's too much gas in a block, there's too much data, then the miners get crippled and it doesn't accurately reflect what the network can handle. So by letting the miners vote, there's sort of a variation in the gas limit, and as a result, the block sizes. So there's this kind of variability, which is advantageous in many ways, but as you'll see in the shortcoming sections, may become a bit of a problem very soon, or it already is a problem, I should say. Ethereum mining is currently proof of work, but it will transition to proof of stake rather soon. And if you don't know what proof of stake is, I'll have a nicer explanation very soon. The hashing algorithm that Ethereum uses is SHA-3 related. So Bitcoin's 256. SHA-3 was meant to be this kind of successor that the National Institute of Standards and Technology kind of pushed for. If you're really into cryptography, you can look at Dagger Hashimoto, which is sort of the name of the actual algorithm there. But the idea is that it's designed intentionally to deter custom miners or these ASIC chips from being implemented. And the way they do that is by being very memory intensive. So you got to remember that these computer chips have limited space, and the more space you use up, the more expensive it becomes. So memory is one of the most sort of space consuming things you can have on a chip. So by forcing the algorithm to, by forcing this hashing process to be memory intensive, you kind of deter the market from deciding, okay, we're going to build these chips. Although, as you see in the picture below, this has been thwarted, but it's not a concern, as you'll soon see. I put this in quote here. It's the idea of a difficulty bomb. And this is implemented in the Ethereum code to deter a centralization of power. And the way that works is that at some specified number of blocks, so maybe after 10,000 or after 30,000 blocks, the difficulty will grow, like it skyrockets. So you might go from a difficulty of, I'm using arbitrary units here, from 100 to 10,000. So now you generate less currency, but it's harder to centralize your power around that. Unlike Bitcoin, which has a very, I think it's like the 2-week sort of difficulty adjustment system, this is just meant to kind of keep everyone on their heels and prevent someone from amassing a bunch of mining power solely for profit. So ASIC miners do exist, but the market research has shown that the profit margin as of now is too narrow for many people to really invest towards this hardware and do anything potentially threatening. And one last sort of unique feature here is this idea of uncles, or I think I call them Ommers. It might be a Nordic origin. I might have that pronunciation incorrect. But it's, as I mentioned in the very beginning, it's highly possible that 2 valid blocks will be submitted simultaneously. So we in our minds, an ideal blockchain is just one sort of continuous chain with blocks, pinned together. Or pinned subsequently, pinned in sequence. Excuse me, I'm getting ahead of myself here. But every now and then, because there are so many people using the network, you will get 2 blocks submitted at the same time, and they're both valid. They're both equally valid. They meet the criteria of being accepted. And the traditional idea here is that the longest chain becomes the valid one, and the other one is orphaned. Like, okay, it's like we just forget about it. It becomes, so you get no reward for working on those side chains. So yeah, traditionally miners just didn't get rewarded. But in Ethereum, these orphans are called uncles, and you get a reduced reward if you were working on one of these Ommer or uncle chains. And the idea behind rewarding this is to deter Bitcoin-like pooling. So you know that for Bitcoin mining, people will get into these massive pools. Bitcoin is susceptible to the 51% attack, and there have been like known cases where pools have gained so much power they hit that 51% mark, although out of goodwill they have decided to intentionally cut back to 49% or less. But the idea by rewarding people who still work on these unused chains is that people won't be willing as much to pool together, because you still get a reward even if you were on the wrong side. So the pooling, the motivation to pool resources together is significantly hampered there. Now, with all of this, all these bells and whistles, Ethereum still has a number of shortcomings. It's not a perfect technology by any means, although it has, opened the gateway for many interesting applications, and has sort of revolutionized the kind of crypto environment here. And I want to start off with the scalability trilemma. And this is also an idea by Vitalik Buterin. And it's that every blockchain has, 3 things it aspires or wants, which are decentralization, security, and scalability. But the problem is, for every blockchain in existence, you can only have 2 out of the 3. So I can have decentralization and security like Bitcoin, but I cannot have scalability. And as you'll notice from more concerning headlines, the Bitcoin blockchain has grown. It's very bloated. And it's also, the more people who make transactions on Bitcoin, the slower things seem to get. If I remember correctly, we're capped at like 21 or less transactions per second for Bitcoin, whereas like Visa can handle 10 million in a second. So that brings me to speed. Ethereum is not designed for high performance applications. And this goes back to what I mentioned earlier, concurrency versus parallelism. Ethereum can run everything at the same time for very high fault tolerance, but it cannot split up a payload and choose specific nodes to do work. So if you're trying to look for like, simulating molecules, Ethereum is not your best bet. The immutability here, immutability is, it's always been crowned as one of the tenets that every blockchain needs to have. And that's true. It is advantageous because it prevents people from editing things that they're not supposed to, or to commit fraud. But there have been there's a very notable case where this sort of backfires in the Ethereum environment. And also those smart contracts I mentioned, these decentralized applications that are based on smart contracts have a major shortcoming, which is that you can't really upgrade them. You have to like destroy the smart contract, and then you have to launch a new one and sort of reroute everyone to the new one. And that's part of trying to stay in line with this immutability. So as an example, the apps on our smartphones, if the developer finds a bug, no sweat, I just push an update. But if there's a bug in a smart contract, tough luck. You have to destroy the contract, and people may have lost money at the time. There's no way to edit that. And I also, that also goes to this sort of explosive growth that I'm talking about. So with all these smart contracts and all of these decentralized applications on top of normal Ether transactions, you now see a bunch of stuff with regards to, these applications that want to put data on the blockchain. So with the variable block size I mentioned, the fast block generation, and the smart contract data on top of all your traditional transactions, we're seeing the growth has been exponential or super exponential. And as a result, the chain is already, greater than 1 terabyte, and it deters people from creating nodes, because that means I, as an enthusiast or as someone who would like to support the network, I have to invest in all this hardware just to, help protect the network and enforce the protocols. And the last problem, I want you guys, like, if you take away one thing from this presentation, even if you don't, even if you're not a big fan of Ethereum, you should be aware of this as like Neo and other smart contract platforms exist, is the Oracle problem. Smart contracts can't get data about the outside world. So what this means is, let's say I wanted a contract that would give all of you maybe 1 Ether if it rains in the next 30 seconds. I have to have some way of letting the node know, like, okay, it's going to rain, the time. And these are historically difficult things to do because all the data that goes onto a blockchain has to be verifiable. You have to have some way of proving over and over and over that this was true. But with oracles, you know, I can't just have one oracle. I need to like have some kind of consensus, but then I have to have a whole like network based on how to, you know, like check the rain, and there has to be some way to vote. And as a result, it is fundamentally incompatible with the blockchain methodology of constant verification and immutability. So this is something that remains unanswered, although there's a lot of research. It's a very speculative field over how one could resolve this. And I mentioned this immutability problem here. I actually wanted to, let's see, I still have some time here. I wanted to go over this very quickly. This is something that is haunted for Ethereum's the entirety of Ethereum's existence. The DAO incident has always come to haunt the Ethereum community. So how a DAO usually gets started is that a smart contract gets created with the initial logic to take in Ether for the exchange of tokens. So this is sort of like if I go on my bank account now and I buy shares in a stock, shares in a company, excuse me. And those tokens that you get for giving your Ether away represent voting rights for that organization. So usually you have maybe a month or 2 weeks, a period of time where people just shell out Ether to get these tokens. And then that purchase period ends and the DAO will begin operation. So there was a DAO called the DAO, literally. That's why I put it in quotes. But there was a flaw. There was a bug that was identified in this kind of exchange logic, and a hacker managed to siphon away millions of dollars worth of Ethereum cryptocurrency. And the entire community was in a panic. And the users to this day are still split. So one approach is leave everything as is. So all the people who paid for the tokens, they don't get their money back, and the network just continues operating as normal. And this is just, you know, to live within those rules of immutability. Because one of the things that people don't like about blockchain hard forks is it's a reminder that the control over the blockchain is still with the developers. It's still, you know, centralized to a degree for the sake of maintenance and security. Another half of the community was like, let's attempt to do a hard fork. So we invalidate all the transactions that surrounded that, that DAO, and people will get their money back. But by doing that, you've essentially shown to the entire community, like, hey, you know, I'm Vitalik Buterin. If there's something I don't like, I can make your data invalid. I can violate immutability, which is terrible. And Cameron, Cameron has a humorous quip here. I have an answer to the Oracle problem. It's just not decentralized. And that is, unfortunately, would not be considered an acceptable answer, because for those oracles to, you know, integrate with the blockchain, there has to be, or people need to see some sense of decentralization, because we don't want to implicitly trust a single entity. That is the bane of blockchain technology. So, you know, going back to the DAO incident, with that being said, if you look right now, there are actually 2 versions of Ethereum. There's Ethereum, like the mainstream version, and then there's Ethereum Classic. And Classic was like, okay, we're not going to fork, and we're just going to leave things, or we will fork, and you know, we'll keep our money. So that's the split that I'm talking about. And this is just a cautionary tale about how, you know, you should be very careful developing these smart contracts and wrestling with the immutability that this platform provides. Now, before I wrap things up, you know, I mentioned all this bad stuff about Ethereum. So I think we should end on a positive note here, that Ethereum is still, you know, very much being actively developed. And that's what I want to talk about with version 2.0. So I mentioned that Ethereum has plenty of milestones. So one of those milestones is a code named Serenity. And Serenity is a full shift to proof of stake. So the idea behind proof of stake, or POS, is that instead of people having to waste electricity and hardware and money to mine coins or to do these repetitive calculations, you will lock up your ether. So I kind of waive my right to my money, and to get the chance to validate transactions. And false transactions, or if you are caught invalidating or like pushing false information, will cause you to lose ether. So the other nodes will essentially punish you and revoke your right to the ether you locked up. So there is an incentive not to lie or not to falsify information. Proof of stake is very advantageous because you don't need all that custom hardware. You're not wasting all that energy. I mean, I think if you look at like the current Bitcoin power expenditure for mining, it's almost like the equivalent of a small country at this point. It's pretty scary stuff. But the problem, a drawback with proof of stake is that you still go back to that hoarding problem. So there are whales and some people will inevitably like have 1 million ether and they'll just keep amassing more and more ether because proof of stake rewards staking by giving you more ether. So in a sense, you haven't really fully resolved that centralization problem. There's also this idea, this is a very, very new, it's still under development and very much in research, are shard chains. So instead of having one main blockchain that all the nodes have to kind of follow with and do their computing on, we redistribute chunks of that main chain to other nodes for faster processing. And this is very tantalizing, tantalizing hints of parallelism. So we have concurrency, but with this, it might be possible to create more computationally intensive applications on the Ethereum chain. Before I get to Beacon Chain, let me look at Zach's question here. If you lock up your ether to have proof of stake, do you still get a small reward just like the miners, or do you purely do it because you're an Ethereum enthusiast and want to help keep it decentralized? You still very much get a reward. You are still rewarded for giving away your right to that currency, so you can't move it or touch it, because then you become like a validator. So you're busy signing off on these blockchains. So yes, you're still rewarded. It's not just for enthusiasts. I mean, there will be inevitably people or institutions that are more than willing to contribute to this staking process for the sanctity of the security of the network. So that's an excellent question. And with that the Beacon chain here. So if we're taking a blockchain and we cut it up and send it off to other nodes, so the nodes are no longer like all in agreement, there has to be a way to kind of make sure they're not like, fibbing their data or they're making things up. So there's a secondary chain called the Beacon chain that is there to try and synchronize all of these shards and allow them to reach a consensus. So this is sort of like, I think of it like scratch paper when you're doing a test. It's like, okay, I'll verify on scratch paper and then I'll put the final result on the exam. So the exam being the main blockchain. So very much, a lot of great stuff in store for 2.0. And with that being said, leaving on that positive note, I hope you've learned a great deal about Ethereum, and I thank you all for your time. Now let me go ahead and I'll stop sharing. I see some questions here, so I'm going to go ahead and okay, looks like my webcam is on. Great. So let's see. There's a question here from Jonathan. How safe is staking Ethereum? Is there a possibility it won't be unlocked ever? The only way that could happen is if somehow during the staking process, you manage to lose your cryptographic keys to your account. So as long as you don't, publish your keys online or let anyone else tamper with it, it's incredibly unlikely. This is almost the same degree of likeliness that someone will encounter a hash collision in the SHA-256 hashing protocol. So it's a rather safe thing to do because theoretically someone could compromise your computer, but it's up to you to keep those keys as secure as possible, because the staking is represented by activity on the blockchain. It's not something your computer is contributing any intensive sort of computational power towards. Does proof of stake still require miners? Or what happens to everyone who is doing lots of mining if they no longer have to do a bunch of pointless hashing for proof of work? I think what happens is, if I remember correctly, the stakers, let's see, proof of stake, in a 100% proof of stake environment, there will be no more mining. essentially it just, they don't really get incentivized anymore to continue that mining process. Luckily, one of the things with Ethereum is that most people are doing GPU mining. So the thing with the GPUs is that they're not catered for Ethereum. There are plenty of other cryptos they can migrate to. So that's almost like an inbuilt benefit, an unthought benefit of how Ethereum has been so adamant in deterring the centralization that you see in Bitcoin and other currencies, where you might witness like the ASICs that I mentioned. Even though they exist, they take up such a small portion of the market because they are not as profitable as what Bitcoin has become. But yeah, that's an excellent question. What happens to the miners? They will essentially, I believe they will not be rewarded once that switch happens, because you don't want people to still be expending all this electricity and resources on something that is being actively deterred via proof of stake. But yes, those are all excellent questions. It's all really good stuff. I'm very happy to answer them and happy to see the interest in this technology.
Excellent talk. Wonderful job. And so the proof of stake that you kind of ended, that's a very exciting, I think, a new types of protocol. We're actually going to have few sessions just fully dedicated to proof of stake. We are also going to have few sessions dedicated purely to sharding as well too. And one of the, even the project that we proposed, the Cerberus, is a sharding protocol that we have been developing here in our lab as well. We actually have 3 different sharding protocols, but the one publicly available one is the Cerberus protocol, which is done in a collaboration with the Radix team, the Radix blockchain. So, and in terms of the mining of the proof of stake, sure, you're not going to do your traditional mining of solving kind of a random puzzle, but there still will be incentivized. And so there is a protocol that allow incentivizing the node to join. And I think maybe one way to think about the proof of stake is that you essentially put your account into a saving account and you gain interest. And that interest is for you be able to signing off those transactions as a validator. So the incentive is still going to be there, but it's going to have a different flavor. I think the other interesting point that you mentioned with regards to concurrency and parallelism kind of put it in from the database perspective is that what we really, so in a database sense, as you pointed out, there is not much of a parallelism because we just have redundancy. We have redundancy running the same contract on different machines. So it's not going to give us any improvement in terms of performance because it's not that we're breaking the same task, dividing it up into 5 pieces so we can do it faster. We'll just have the same task and run it 5 times. So we'll just get redundancy. So it's a more kind of a redundancy as opposed to being in the parallel. In concurrency, again, so for us, for the database theory, the concurrency means you could still have parallelism. So concurrency really means you concurrently executing transaction at the same time. And if the hardware allows parallelism and those transactions can be in fact run in parallel without any conflict, so you do get parallelism there as well too. But well, in this case, it's really the question of redundancy. We're just simply redundantly running the same task in every machine. So as John said, there is no really gain, and there is not. The parallelism provides durability as opposed to performance, or reliability as opposed to performance.
Right, absolutely.
So any question? Again, there was a very exciting, very energetic speaker, and I think, yeah, I always like listening to John, and he teaches on different topics, so it was excellent. I personally enjoyed it very much.
Thank you so much for having me, and thank you to everyone for attending and asking such wonderful questions. I greatly appreciate the opportunity.